started. I'm missing somebody. But anyway. Any questions before I get started? I think that it's a good idea to catch up on what we did from last week and before we get started on the new material. This one, you could have done it a number of different ways. It was just to get a little bit of practice with summation and product signs. But it's a good thing to do something like this, is to define what x1, x2, x3, and x4 is just for future reference. And it's just, and it doesn't matter how you do it, but you can do it just in the order presented, 43, 16, 10, and 9. Like that. And then just expand each one of the summation of product signs and go ahead and calculate the value. Did anybody have any questions about this? I think it's pretty straightforward. It's just to give you an idea of navigating around them. Just to give you an example of this one, the summation is summation of xi squared over xy is equal to x1 squared over x1 plus x2 squared over x2 plus x3 squared over x3 plus x4 squared over x4, whereas the product of xi squared over xy is x1 squared over x1 times x2 squared over x2 times x3 squared over x3 times x4 squared over x4. And obviously it's going to be different results. That's all that there was to those. So, yes?
Was the -8 over 2, was that the noise reduction rating rule of thumb?
No,
or does that have any other, because that's exactly what it is.
It was just dumb luck on my part, because I just made it up off the top of my head. No, so that, but I'm glad that it actually means something.
It does, actually. Yeah.
Was that for my age? Did you use that? Okay. Then the combinatorics with large numbers. I'll just do the second one. Okay. So 5,000 objects taken 2 at a time. Is 5,000 factorial over 5,000 minus 2 factorial, 2 factorial. So that would be 5,000 times 4,999 times 4,998 factorial over 2 factorial times 4,998 factorial. Those cancel out. Is that, no, all you have to do is multiply 2,500 times 4,999, and you get the answer, which is 12,497,500, and I'm pretty sure that comes up to that result. So I multiply that out just to make sure that I didn't make a mistake. 2,500 times 4,999.
Can you do that simplification one more time?
Sure. Let's make sure that I get the right answer before I go any further. It is right. Okay. Yeah, I'll do that again. So 5,000 factorial is 5,000 times 4,999 times 4,998 factorial. Right? And this is 2 factorial, which is 2 times 4,998 factorial. So those two cancel. This one is reduced to 2,500, so you just 2,500 times 4,999. Does that help?
Okay, so is that a 2 factorial in the parentheses on the bottom? Or just 5,000 minus 2?
5,000 minus 2. So that's 4,998
Okay.
factorial. That's what you're trying to isolate.
Okay, if it was 5 over 3, would it be 5,000 minus 3 factorial?
So 5,000 taking 3 objects at a time?
Yes.
Okay. That would be that would be 5,000 times 4,999 times 4,998 times 4,997 factorial over 3 times 2, 3 factorial is 6 times 4,997 factorial, which is that. So those would cancel out. And then you find where 6 would factor into that. Probably factor into this, so that's 8. And 19 is 8.
3.
Yeah, so that's 888.
No, 833.
3. That's right. 833. See, I'm terrible at doing stuff in my head. That's why
And then just multiply those 3.
and just multiply those 3 out. Yeah. That makes sense?
Yep.
Everybody else? Okay. Who's missing today? Lauder's missing. Dahlia, that's right.
Usually San Antonio.
Okay. All right. So that's the combinatorics, and this one is the same thing, just 1,000 instead of 5,000. And then the next one, not particularly hard, but tedious. So I did, wrong one, Venn diagram. Okay, so let's take a look at the Venn diagram first. This is where I said that there were 200 students in the program, so that's omega, that's the universe, right? And then 50 in aviation safety, 30 in occupational, and 60 that are pilots. And then 25 pilots that are also interested in aviation safety, so that's the intersection, and 10 pilots that are primarily interested in occupational safety, so that's the intersection of those two. Okay. So the way I envision that is that here's our 60 pilots, here's our 50 aviation safety people, and here's our 30 occupational safety people, and then there's the 10 pilots who are interested in occupational and the 25 who are interested in aviation. So this represents the intersection. And what's left here is the number who are only, who don't intersect with either of the other two. So I had to subtract 10 from 30 to get that 20, and then 35 from 60 to get 25, and then 25 from 50 to get 25 that are left behind. And that's our universe right there. So the probabilities of each, based on that Venn diagram, is that too small for everybody to see? See that okay?
Mm-hmm.
So, the probabilities then, aviation safety, 50 out of 200, occupational, 30 out of 200, pilot, 60 out of 200, and then pilot N is the intersection. Pilot N interested in aviation safety is 25 out of 200, and pilot N interested in occupational safety is 10 out of 200, primarily interested in occupational safety and aviation safety. There's no intersection of the two. That it would have had to have looked like kind of like the Olympic symbol, but -2. Okay, wasn't there an old beer symbol that looked like that? But anyway, there's some. I'm sorry.
It's random.
Yeah, that's right. But it would have looked like that, but it didn't, since there's no interaction. There's no intersection between two occupational, somebody who's interested in both types of safety. So that's the null set, 0 to 200. And then we start getting into the unions, pilot or aviation. Okay, so you have to take the probability of being a pilot, which we already have, the probability of being in aviation, which we already have, and then the intersection. So that's why I asked you those in the order that I did. The intersection of pilot and aviation. Okay, pilot or occupational is, we have both of those, and then this intersection, and likewise the pilot or occupational, occupational or aviation, sorry. And since the null, that's the null set, it's just the addition of those two. So far, so good? Like I said, it's not particularly hard, it's just tedious. If a student is a pilot, what is the probability that that student is primarily interested in occupational? So these are conditional then. Remember that the conditional for pilot is equal to either and that's what I'm exploiting here, the pilot has a probability of aviation given that you're a pilot, and it's also equal to probability of occupational that you're a pilot. So that's what these two come from, and we know the intersection, or I'm sorry, backwards. But since we know this, and we know this, we just solve it for those to get both of these relationships here in order to get those probabilities. And so it's just a matter of manipulating the intersection and conditional probability equations. And then finally, I did the same thing then for all of them, and it's the same relationship. So we have pilot intersect with occupational, and you can solve for the conditional probability. Aviation intersect with occupational, and that conditional probability, and likewise for the aviation intersect with occupational, aviation intersect with pilot. Make sense?
Mm-hmm.
Like I said, tedious, but not particularly difficult. Any questions about that? No? All right. Okay, well, let's take a look at Bayes' theorem. Okay, so Bayes' theorem. So let's go take a look at B for a minute. So for the probability of A, and that's this area in the middle here, whatever it might be, is essentially equal to the summation of the probability of A intersect with B sub I. And then the probability of A intersect with B sub I, each one uses the relationship that it's probability of A times the probability of B sub I given A, which is this one right here, or its probability of B sub I times the probability of a given piece of I. And we can exploit those two relationships as well. So that when you get, so that you can take v sub I given A and reduce that to A intersects, because using this relationship right here, you have probability of A intersect v sub I, or probability of A. And you can then make that equal to A intersect v sub I equal to this relationship right here. Over this summation. Then when you encounter a problem, you can take that generic form of the problem and determine for the engine parts what you're going to assign to A and what you're going to assign to each one of the subsections. So here we have an engine part is purchased from 2 suppliers, so that means that we have 2 sections, and those 2 sections of our I'm trying to draw those two sections are suppliers A and B, and then the failures are the subset that intersect both A and B. Okay, so supplier A and supplier B are the 2 sections. The probability of failure given supplier A, we know that 15% of those fail, so the probability of failure given that we know that some comes from supplier A is 0.15, and we know the probability of failure of B. So the first thing we want to figure out is the probability of failure overall. So we know the failure given supplier sub I, and we know the probability of supplier sub I. So that reduces to probability of failure is, if we expand this, failure given supplier A. Now use the shorthand here, so I don't have to write all that out. S sub A over probability of S sub A, and then probability of failure given given S sub B over the probability of S sub B. And we know the probability of failures because we know the failure given supplier A is 0.15. And the probability of supplier A is 0.4. Probability of failure given supplier B is 0.25. And the probability of supplier B is 0.6. And that should come out to the overall probability of failure being 0.21. Okay. Then, so for that, what we're doing is we're exploiting.
Excuse me?
So
Looks like it's wrong.
what part of it's wrong?
We have to multiply these 2 elements.
Oh, yeah. Yeah, so this is the part that has to be summed first before you multiply it. But wait a minute. Did I write that incorrectly?
Because that comes out at 0.7.
Yeah. Oh, it's multiplication. looking at my own, so it's probability of failure in supplier A times probability of supplier A plus the probability of failure given supplier B times the probability of supplier B. Okay, so it's right numbers, you don't divide by it. So 0.15 times 0.4 plus 0.25 times 0.6. And that's 0.21. Thank you. So doing that then, you exploit this relationship, the probability of failure, exploit this relationship right here, because A intersect B sub I expands to this right here, A given B sub I times B sub I. It's the same type of a relationship there. Okay? So then, the other way, if we know that we have a failure, given that we are looking at supplier, if we know we have a failure, what's the probability that it comes from supplier A? You take the relationship of these two right here, because we know that now the probability of supplier, we know this, we know that that it is, we know this one because we know that what each one of the suppliers' probabilities are, and we know the probability of failure given the supplier. Okay, so we know this one right here, so all we need to do is solve for that. And so this is probability of failure times the supplier A times, here, let me write it out so it's a little bit clearer. Because right here, what we have is probability of failure, supplier A given its failure. The probability of failure is equal to the probability of failure given supplier A times probability of supplier A. Okay, so we've already calculated what the probability of failure is. So we know this one. As far as the probability of failure given to the supplier A, we know that one. And we know what the probability of supplier A is, so all you need to do is solve for this. And it comes from this relationship right here. Okay? And likewise, use the same thing for B. And that comes from this relationship also. So you just enumerate what you know, and then solve for the one that you don't know. Solve for the single unknown, and you can get those probabilities then. So, and also think about the face validity of it. What's the probability that it comes from supplier A, given that I know that I have a failed part? Well, we have fewer things, that only 40% come from supplier A, and 60% come from supplier B, so I would expect the probabilities for this conditional probability to be lower than for this conditional probability. And also based on the fact that there are more parts come from supplier B, and a higher percentage of the parts are failures that come from supplier B. So those together would indicate that or would imply that I'm going to get a higher probability than I am for the first conditional probability relationship. Making sense so far? Kind of. This is really what I do, and I think I put this on the equation sheet. But this is the source for all of that. What you have to do is draw your diagram, like this, and then make the relationship with these generic A's and B sub i's. Okay, A is the probability of failure in this case. B sub I is supplier A and supplier B probabilities. Once you've done that, once you've made the Venn diagram, once you've made that equivalent, then you can go ahead and start substituting and manipulate those equations. Would it be helpful if I put in the actual probabilities here, the numbers? Or does everybody see where the numbers came from? Sure. So if I take this one, this is the first question here. So the probability of supplier A, I need to take, given that it's a failure, is equal to the probability of failure given that supplier A times the probability that comes from supplier A over the probability of failure. Okay. So, given the failure given that it comes from supplier A is 0.4. Or I'm sorry, 0.15. And the probability that it comes from supplier A is 0.4. And the probability of failure, if you got from right here, is 0.21. And that should come out to 0.2857. Check my arithmetic to make sure that I'm making mistakes there. Okay. And it's the same process for supplier B. And those numbers are, the probability that it's a failure, that it comes from supplier B is 0.25. Probability that it comes from supplier B is 0.6. And the overall probability of failure is 0.21. Yes.
This may be going beyond the scope of what you're trying to show us, but if it was, say we had 3 suppliers,
Mm-hmm.
how would we figure out if it was, say, supplier A or C? Like, what is the probability that the failure came from A or C?
Oh.
Is that something you're going to ask us, or am I just...
No, that's not something I would ask you, because what you need to do there is look for an A or C is a union. So that would be, if there's no, all you have to do with that is the probability of a failure given A, and plus the failure given B, because they will never come from both. You see what I mean? So you just add those two
So
probabilities
it's
up.
just the two together?
Yeah, yeah. Because there's no intersection. Actually, that's a good question. I didn't think about it. Because you could get it from this, right? And just recognize that there's no intersection. It becomes just an addition problem.
Don't ask that, it doesn't mean anything.
Yeah. It'll just come into my mind. I won't know where it came from. Happens a lot. Other questions before I don't want to skip over this, because this base theorem isn't overly obvious, but it's useful nevertheless. Okay, well, why don't we come back to it and come up with something. Let's go to the next one. tree diagram for 4 consecutive renewable trials with a probability failure on any trial is 0.2. Well, this is, if you try to do it, you know that this is tedious beyond comparison, so I'm not going to draw it out. I'm going to show you my Excel. It was just going one beyond what we did in class. First of all, you know that 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. You know there's going to be 16 branches. So that's where you start out with. I'm going to shrink this a little. So you're going to have 16 branches. Assume that P is 0.2 or failure. You could have done it the other way around, it's just as fine, you would just invert the whole thing. And then go through the tedious process of multiplying each branch, you get 16 outcomes. However, if you notice by enumeration, there's a number of different ways to get 3 P's and 1 Q, or 4 P's and 1 Q. And so all the yellows are 3 P's and 1 Q, all the sort of pinkish ones are 2 P's and 2 Q's, and then the blue one is 1 P and 3 Q's, and that's it. Other than the 4 P's and 1 Q, or 0 Q's and 0 P's and 4 Q's, we have 4 different colors. The yellows, the pinks, the blues, 3 different colors, sorry. Yellows, pinks, blues. And
no color.
And no color. The no color is the ones that are the only one path. That's a 0 and 4. And by enumeration, you can add up the 4 ways you can get 3 P's and 1 Q, the 4 ways you can get 2 P's and 2 Q's, 1, 2, 3, 4, 5, 6, and the 3 ways you can get 1 P and 3 Q's. Now, you can also look at the combinations. If you look at the random variable as being, let's look at the random variable being the number of Q's. So we can get 0, 1, 2, 3, or 4. So what we end up with then is, we did this 4 times, so it's 4 objects taken 0 at a time, 4 objects taken 1 at a time, and this is 4 objects taken 2 at a time, 4 objects taken 3 at a time, 4 objects taken 4 at a time. Okay, so this becomes 1, this becomes 1, because if you have 0 at a time or 1 at a time, it always becomes 1, because, let me demonstrate it, because you have 4 factorial over 4 minus 0 factorial over 4 factorial, okay? Over 0 factorial, I'm sorry. So this is 4 factorial over 4 factorial equals 1. This is 4 factorial over 4 minus 1 factorial, 1 factorial. So that ends up being 4. That ends up being 4. And if we count the number with 1 Q, 1, 2, 3, 4. Okay. 4 objects taken 2 at a time, 4 factorial over 4 minus 2 factorial, 2 factorial, that's 4 is 3 is first 12 is 6, and then 4 factorial over 3 factorial is 4 minus 3 factorial, 3 factorial, and you end up with 4 again. And then 4 taken 4 minus 4 factorial times 4 factorial ends up with 1. And that's where we get the coefficients for the 3 P's, 1 Q is 4, 2 P's and 2 Q's, which is this right here, is 6. It's 1, 2, 3, 4, 5, 6. And then once again with the 1 P and 3 Q's, it's 4 right here. And the 0 P's and 4 Q's is that coefficient right there. And it tells you the number of times you have to multiply each one of those combinations. And so the idea is the number of errors, but it doesn't matter. You can they're symmetrical. You can do it either way. You get exactly the same result, and it's the same way as doing the binomial, or the probability of 0 P's and 0 Q's. So if we did the probability of 0 Q's, this would, let's just do this one. Probability of 2 P's and 2 Q's. That would be probability of x equals 2, and that would, and that comes out to 4 objects taken 2 at a time, p to the x. And objects taken x at a time, p to the x, 1 minus p to the n minus x, and that's 4 objects taken 2 at a time, p to the squared, and 1 minus p, and p in this case is 0.8, and 1 minus p up to 2 is squared, and so 0.8 squared times 0.2 squared over 4 objects taken 2 at a time is 6, and you should end up with this 0.1536.
You use the binomial probability distribution on that one, because it's one or the other.
Yeah, and that's what I'm trying to demonstrate with this is that the binomial precludes us having to do this kind of a tree diagram, but this is where the binomial comes from. Because the binomial is sequential Bernoulli trials, which is exactly what this is demonstrating. Multiply that and make sure that I got it right. 4, 8. 4, 8 times 6. 0.04 times 0.16 times 6. What's 0.16 times 0.04?
1064.
Okay, then that's where I made the mistake.
No, the 0.64.
Where
Where you squared your 0.8.
it is 16. Oh, okay. Yeah. There we go. That's more like it. I should never do arithmetic in my head. Okay, so that should look a little bit better. 0.1536.
1.536.
1536.
1.
No, it shouldn't be. Okay, well, 0.8 squared is 0.64, correct? And 0.2 squared is 0.04.
Oh,
And 6 times that product.
okay, I know.
Okay. On me this time, that's good. All right. So, the point of all this is to show you how sequential Bernoulli trials can be, you can enumerate it and get the same result as using the binomial, because that's what the binomial does, is it takes sequential Bernoulli trials, and anything beyond this becomes completely unwieldy. I mean, this is ugly enough as it is with just 4 sequential, and if we have anything more than 4 sequential Bernoulli trials, you know, we have 20 launches, or 20 attempts to do something, this would expand way out and become unwieldy. But the Bernoulli, this is what the Bernoulli, or the binomial distribution does, is it takes the sequential Bernoulli trials and gives you a method, a formula by which to calculate it, which essentially does this. Does it make sense? The derivation. Okay. And did I say to stop there?
No.
Six, A and B.
A and B. I said A and B. Okay. Okay. Last 100 flights in an aircraft, there were 6 engine failures, find the following. So probability of failure equals 6 over 100, or 0.06. Right? So what is the probability of failure on the next flight? That's just a single Bernoulli trial, so that's 0.06. It's just a single Bernoulli trial. Next 8 flights, what is the probability of no failures? Okay, what is the probability of at least 1 failure? Okay, so this is binomial, probability of no failures. Okay, so that would be the probability of x equals 0. And that's an object's taken x at a time. So in this case, n was equal to, what did I say, 10? 8. 8. So n objects taken x at a time, p to the x, minus p to the n minus x. So that's 8 objects taken 0 at a time. We know that goes to 1. P, which the probability of failure is 0.06 to the x, which is 0. And then 1 minus p is 0.94 to the n minus x, which is 8. So that goes to 1, that goes to 1, 0.94 to the 8, and I forget what that was. It's is 0.6, essentially 0.61. Since we have relatively low probability of failure, that makes sense that we could do 8 of them and still have better than 50-50 chance of not having any failures. And then finally, I said the probability of at least 1 failure. So since you've already calculated this, it's 1 minus 0.61 essentially, or 0.39. Okay, or you can go brute force it and do all the other 8 and add them up. But it's a complement of that. So on the exam, I wouldn't do that. I just 1 minus, which you already found.
You get roughly the same answer if you add them all up, or?
Mm-hmm. Yeah, because this let me look at it, see what I did. I added them up. No, I didn't. So let's add them up. You should get exactly the same answer.
Yep.
Mm-hmm. Let's do it for the same significant digits. Okay. 8 is not 9. No, it wasn't. It must have been 10. Yeah, identical. And it should give you the identical answer. And for a question like this, don't give me more than 2 significant digits, that's plenty. If you told me 0.61 and that the complementary probability is 0.39, that's perfectly fine. Don't I know your calculators will go out to 10, but don't give me 10. It's not really pertinent. Okay? That's the Bernoulli and binomial distributions. So, for next week, after today's lecture, hopefully, we should be able to do C through H, 7, 8, 9, and 10, and 11. All of those. We'll talk about that and practice problem set next week. Again, remember that I scheduled the first exam for 2 weeks. Depending on how far we get today, I can be flexible, especially with a small class like this. And I don't think it's going to be particularly detrimental for the rest of the semester if we push the exam back and do it later. But for now, that's what I scheduled. Okay, let us talk about one more probability distribution or so, then we can take a break. So we talked about the binomial. The next one is the Poisson distribution. Okay. The Poisson distribution has no upper bound. Okay. That's what's interesting about it. Because the Poisson process is something that happens, you measure occurrences of an event, and you measure them into perpetuity. Okay. The probability, the number of times this happened, theoretically to infinity. However, the way we calculate the parameter, and the parameter here is lambda, which is kind of like p in the binomial distribution. It's the mean occurrence rate per unit time. So let's say that I have been measuring this for the past 2 years. Okay. But it might be more interesting for me to measure the occurrence per hour, or per 100 hours. Okay, that's my exposure times 100 hours. So what I do is I normalize it to 100 hours. So if I had over 2 years, okay.
So you said there could be no time limit,
Theoretically,
potentially?
yeah, it's from now until into perpetuity, theoretically. But let's say I get 2 years worth of data. Okay, so 2 years equals 365 days, and there are 24 hours. So 1 day is 24 hours, and the other way around. It's 24 hours in 1 day. So what's 365 times? What's 365 times 24 times 2? Somebody multiply that out for me. That's the number of hours in 2 years. That's what I'm getting at.
17,520.
17,520. Okay, so let's say I measured, in 17,520, I measured 562 occurrences. Whatever it is, doesn't matter. So 562 instances in 17,520 hours. But my unit of exposure that I'm interested in is per, let's say per 100 hours. Okay. This is just like standardizing to 200,000 work hours. Okay, so I get X occurrences per 100 hours when I know that. Okay, so what I need to do is take this and multiply it by 3.2. Okay. Thank you. So X equals 3.2 occurrences per 100 hours. That's my lambda. Okay, that's my lambda equals 3.2. Okay, if that's my unit of exposure that I'm interested in, 100 hours. Then what's what is 1 over 3.2? It's a reciprocal of lambda inverse equals, somebody, the calculator. I'm definitely, I can't square 0.8 in my head, so I'm looking,
0.3,
I'm sorry,
0.3.
0.3. Okay. So,
Is that lambda over 100 hours in?
this
or
is
that-
X,
That's
but
X over 100 hours,
probably,
and
yeah,
then lambda equals
Yeah.
3.2.
probably it would be a lot better for me just to stick with lambda. So take the X away and call it lambda. Okay. That's probably better. So, if we take our occurrence per 100 hours, it's 3.2 occurrences. Let's say that we measured the failure rate, okay, over 2 years, and the failure rate it fails 3.2 times every 100 hours. That's not very good, but let's just say that that's what it is that we're interested in. Because I can put these machines into operation and measure the failure rate ad nauseam. I mean, or until what they will be is in operation. So let's say I put resistors in, and they measure, and the resistors fail 3.2 every 100 hours. Okay, so that means that, and that's why I did lambda inverse, that every 30 hours I have to replace a resistor, because it's 0.3 times 100. That's the mean time between failure is the inverse of lambda. And so every 30 hours, that tells me, on the average, I'm going to have to replace a resistor, because that's how many times, that's our failure rate over 2 years. Okay? That's why you may measure that over a long period of time, so that you know what the failure rate is. And we can assume that unless we get some drastic change, that we can use that for our lambda. And we can use that for our failure rate. And then the inverse of it is the mean time between failures. And that tells us how long it will operate without failure on the average. So I know that now, and I know that my expected value is lambda times t, whatever our units of operation are going to be. Now, this 2 years was the last 2 years. So now what I want to do is say, okay, I want to project what my how this Poisson process is going to behave over the next, let's say, 100 hours, okay, or the next 30 hours of operation, or the next 1,000 hours of operation, whatever. Okay, so that's my units of contiguous exposure, is my projection into the future. And then my other parameter is the number of events, okay? So now I can say, in the next 1,000 hours of operation, what's the probability of having 10 failures, for instance, okay? And this is the formula for doing that. Lambda is my parameter, T is the hours of projected future operation, X is the number of occurrences of the event of interest. In this case, let's say it's resistor failures, and those are the only 3 that I need. Then it's either the minus lambda t. Notice that lambda t is the parameter that we've calculated, and x factorial in the denominator. We'll come back to the CMF, but you can add subunits of it just like you can with a. This is discrete, so it's just like a binomial distribution. So let's take a look at an example. I'll erase this, because we know where 1750 came from. It's 2 years. And remember that it's lambda t to the x, e to the minus lambda t over x factorial. And that's the probability that x equals little x. Okay? So this is a Poisson process. Like I said, over an infinite number, theoretically infinite number of trials. Then counting the events of interest, and then the expected number of occurrences per unit exposure, and that's our lambda. And these are some examples: defective items, crashes, human errors. All of that stuff is a Poisson process, theoretically. You probably have noticed that there's a pretty close relationship between binomial and Poisson. And Poisson is considered an approximation of a binomial. If you don't have real binomial data, you can approximate it with Poisson because it's more generalizable. The limitation that you run into is that if my lambda is 3.2, that's not going to work because a Poisson has to have a p between 0 and 1 because p is a probability. It's not a failure, it's not a lambda. It's not exactly the same thing, but Poisson does approximate binomial when lambda can be expressed as a probability. So, let's look at our example here. Let's say that I observed 10 events and 1,000 time units. Doesn't matter. Seconds, minutes, hours, days, doesn't matter. But on the average, I observed 10 events and 1,000 time units. So my lambda is 0.01. Now I want to project into the future 500 of those time units, whatever they are. So that means that lambda t is 5. So lambda is 0.01, lambda t is 5. And I can project this into infinity. There is no upper bound. That's why I always have an ellipsis at the end here. I stopped at 90 because I got diminishingly small probabilities, and that's what happens as you get to very large t's. Let's see what I was I got distracted for this moment. But anyway, as soon as you hit 10 here, when you get to 20, diminishingly small, beyond that, it's so small that it doesn't really mean anything. So it doesn't mean too much past 10. However, for each one of those...
Sorry, what does the plot of that look like?
Actually, what happens is that it peaks at lambda t about, so that you would get something that looks like, drawn here.
Yeah, about 4 or 5 there.
So that you would have something, and I'll draw it looking continuous, although this isn't continuous. Well, I'll draw it so it's not continuous. So we end up with something very small, and then it gets a little bit bigger, and a little bit bigger, and then it gets bigger than that, and then it peaks at about lambda t, and then starts getting smaller again, and so on. So this is lambda t, and remember that's the expected value. And that will move back and forth depending on where your lambda t lies. So the way we calculate that is with this equation. So let's take time units. I'm going 500, operating for 500 time units. What's the probability of x of 8 occurrences in the next 500 time units? So the way that would be calculated, probability that x equals 8 is lambda t. Lambda we already know is 0.01. 500 we've determined to be of interest is 500, or t is 500, x is 8, and then e to the minus lambda, 0.01, times t is 500, over x factorial, which is 8 factorial. And if you do the arithmetic on that, you should come out with 0.065. So what that means that if given that I have this lambda, if I choose to operate or choose to project it into the next 500 time units, what's the probability of getting 8 occurrences of this Poisson process? Whether they're errors or failures or arrivals, because like I said, this can be used to model arrivals too, the number of arrivals. And that's actually a very good intuitive way to think about this. Okay? I sit and I watch the number of people that come through the door in a supermarket. Okay, so every day for 8 hours. Now, something you have to watch if you're doing something like that is to make sure that you account for busy times. So if you're at a bank, for instance, chances are you're going to get a lot of people over the noon hour. So that's going to throw your lambda way off. So what you might want to do is do 2 different lambdas. One lambda for the busy time between, say, 11:30 and 1:30. That's my lambda. And then another lambda for the off times, quote unquote off times. Okay, so let's say I watch, that I'm just interested in the arrival rates for the 2 hours between 11:30 and 1:30, or whenever it makes sense. You know, that's a typical time when the bank is busy, 11:30 to 1:30. So I start watching every day at 11:30, and I record the number of people that come through the door. Just count them. That's all you need to do. And then I do that over the course of, I don't know, a month. And then I come back to them. On the average, your lunchtime arrival per hour is. That would be your lambda. Okay? And then I would say, okay, what's the probability of exactly 8 people coming in the next hour? Well, then you would come up with something like this. Okay, well, it's only a 6% probability. But again, you could say, what's the probability that 10 or fewer people will arrive? Well, then I can add all these up. That's a pretty high probability that they're going to arrive in the next hour.
You wouldn't include 0, or would you?
You could, because 10 or fewer it's possible that nobody would come in. It's unlikely, but it's possible. Is that making a little bit more intuitive sense now? What constitutes a Poisson process and what constitutes the Poisson distribution? It's a little bit more flexible than the binomial because it doesn't require a probability. Lambda isn't a probability. It's a rate of occurrence per unit time.
So if your conditions change so much, you're trying to predict something from your original lambda, the original lambda will be rendered useless. If the
It
conditions
could, yeah. If something happens that it's completely different and your lambda doesn't even apply, then yeah, you would have to scrap your lambda. Because the assumption is the lambda is a good estimate of the arrival rate for no matter how long you wait. That if I record the lunchtime traffic for the next 2 weeks, and then I record it again for the 2 weeks after that, it should be similar. But if it's not, and it's not even within, and we'll be doing confidence intervals on lambda, and if it's not even within a reasonable confidence interval, then you probably have to rethink what your lambda will be.
Could you think of that like customs at an international or at an airport with international arrivals? For an hour, no international flights coming, so customs is dead, and then 3 747s arrive, and 1,200 people walk through over the course of an hour, and then no more planes arrive. And so
that's right. You can model that a number of different ways. You can say, okay, this is what you can expect during the busy time, or you can say, and it would have different applications, or you can say, and that would be for staffing. Okay, for instance,
right.
This is what you have during the busy time, or you can say, on the average, this is the number of international arrivals all the time, and that would have a different application than something like staffing. What it might be able to tell you is something like, for instance, let's say the number of international arrivals,
like size of the building they need, or
possibly size of building, or maybe the number of maybe for supply purposes. Because if you can store things, then you supply, visas or whatever.
Right.
Okay, I expect over the next 3 weeks that there are going to be this many people coming through. So so I stock up my paper visas, okay, something like that.
Right.
Yeah.
In this case, why is X equal to 8?
I just arbitrarily picked 8.
Okay.
Just to illustrate how to calculate it. All of these are calculated exactly the same way. But in this case, 8 would mean, what's the probability of exactly 8 occurrences given, in the next 500 time units, given that my lambda is 0.01.
Okay, so the 8 separate from 2 and 5.
Yeah, that's right,
Okay.
yeah, 8 is just one of them that I arbitrarily picked out. Okay. What I'm gonna do when you come back is relate this to the binomial. And so why don't you take 10 minutes, come back, we'll talk about this in the binomial. I thought I